All right, guys, we are going to move on into part 2 of our notes today. So by the end of this video, we'll be halfway through our chapter 5 notes, and we're talking about osmosis. Now, osmosis is the movement of water, so that is why I have a picture of water here. And it shows you that water is moving through this little membrane here. Now, the molecules themselves, the purple dots, they can't fit through that membrane. It's selectively permeable, meaning that it only lets certain things through. And water is going to move in the direction of a higher concentration of solute particles. It's trying to spread those solute particles out. So on the left side here, we don't have as many purple dots as we have on the right side. And the water recognizes that there's a lot more purple dots on this side, so that's why it is moving through the membrane and it looks uneven, but in actuality, it's creating the same amount of space around these molecules as there is around the molecules on the left side. So in diffusion, hold on.
Juniors with the last name F through J, please report to the auditorium with yearbook photos.
In diffusion, solute particles are moved from one side of the cell to the other side. Osmosis is very similar to diffusion, where we are going from a high concentration to a low concentration. However, instead of moving the solute particles like we do in diffusion, we're moving the solvent particles. By definition, and we probably went over all this in our vocab already, osmosis is the process by which water molecules diffuse across a cell membrane from an area of higher concentration to an area of lower concentration. Now, like diffusion, osmosis requires no energy, and there is your first note to write down for today. Pay attention just to the red stuff. Now, unlike diffusion, osmosis uses proteins in the cell membrane called aquaporins to move water. This is because water molecules cannot pass through the cell membrane. That cell membrane is nonpolar because of those fatty acid tails, so it refuses to let water pass directly through it, which is why it has to use those special aquaporins. So you have your cell membrane, and in this picture it shows as red and like a tan. And right in the middle, you have these random aquaporins, which kind of guard these fatty acid tails from touching the water. And that is how the water can get in or out of the cell. Your cell membrane is made up of many different kinds of little channel proteins. So aquaporins are just one of them. Now, there are 3 types of osmosis solutions. We have hypotonic, hypertonic, and isotonic. By definition, hypotonic is when the concentration of solute molecules outside the cell is lower than the concentration in the cytosol. Cytosol is just another word for cytoplasm. So, right here we have 1 solute particle outside of the cell, and we have 6 particles inside of the cell. Water is going to chase after the higher concentration. So we want to have the same concentration of solute to solvent on both sides of the cell membrane. Hypotonic solutions make water rush into the cell, and this can cause the cell to swell up and burst because you have so much water being pushed into it. The easiest way for me to remember hypotonic is I think of a hippopotamus, because hippopotamuses are really big, and Pittsburgh Zoo actually just got a pygmy hippo. He's adorable. I saw him over the summer one time. But they, like I said, hippos are really big. Hypo kind of sounds like hippo, so you can try to remember it that way. Now, cytolysis is when too much water is diffusing into the cell, causing it to swell and burst. So instead of continuously saying, oh, the cell is going to swell and burst, we just say the cell goes through cytolysis. Cyto is the prefix for cell, and lysis means to break apart. So it means cell breaking apart. On the opposite side of that, we have hypertonic solution, which is when the concentration of solute molecules outside of the cell is higher than the concentration in the cell. So looking at this picture here, you can see there's only 6 particles in the cell, and there's a lot there outside of the cell. So water is going to chase after that higher concentration, meaning that water is going to leave. Hypertonic solutions make water diffuse out of the cell, and this is going to make the cell shrivel up and become smaller. I used to have a really good friend whenever I was in elementary school, middle school, and even through high school. And she was a really short little girl, but she was very hyper. She always had to be doing something. And hypertonic makes me think of her because she was little, she was short, and the cells get smaller. Isotonic is when the concentration of solutes outside and inside are completely equal. So we have the same number of solute particles outside the cell as we do inside the cell. Isotonic solutions make water diffuse into and out of the cell completely equally. And this keeps the cell the same size because there is no net movement of water. That means that we're not gaining any water and we're not losing any water. So the rate of water moving does not stop. Water is still going to come into the cell, but it's also going to be leaving the cell at the same time. So your cell will stay exactly the same size. And this is the ideal way for your cells to function. Many unicellular freshwater organisms function in a hypotonic environment. So remember, this is going to make water rush into the cell. Think about a hippo that's getting bigger. However, the unicellular organism does not want all this water inside of itself. So that's like an amoeba. They have these little contractile vacuoles which are going to store the water that the organism's taken in. Now, since the organism doesn't want this water because eventually it could go through cytolysis, the contractile vacuole is going to collect it and then pump it back out of the cell. So here we have an amoeba, and this little spot in here is its contractile vacuole, and that it's a pretty large contractile vacuole. It looks like it's about to pop, so it's pretty full. That contractile vacuole is going to squeeze down on itself, and it's going to squirt all that water back out of the cell, and it's going to empty itself back out. And this contractile vacuole, there's a few inside of each one of these cells, and it continuously works. Eukaryotic cells can also function in a hypotonic environment, so I'm talking about multicellular organisms like us. Our vacuoles function differently than unicellular prokaryotic cells because our vacuoles cannot contract. They're simply a storage center. So we have to do something a little bit differently. We have to pump solute particles outside of our cell. Water is going to chase the higher solute concentration, so we're going to push little particles out of our cell, and that is going to make the water leave. So here would be the inside of our cell, and there's a lot of water in there, a lot of water outside, but there's no solute particles out here. So water is actually rushing into our cell right now because we have so much more solute inside the cell. We are going to take those solute particles and we're going to start pushing them back out of our cell. And as we push the solute particles out of our cell, the water is also going to leave. And eventually we'll reach an equilibrium where we have an even number of solute particles to water particles both in and out of the cell. Plant cells, they love hypotonic environments. They really thrive in them. They like it when their cells swell up. Now they have a cell wall, so it's different than a cell membrane, and they aren't really going to pop unless, of course, you're freezing water inside of them, forcing those bonds to get bigger. But most of the time, they like that hypotonic environment because it keeps the plant nice and straight, and it keeps it from wilting. That's what turgor pressure is. It's a pressure that water molecules exert against the cell wall. So here I have two examples of plants. This one has a lot of turgor pressure. He's definitely in a hypotonic environment. He probably just recently got watered. Now this poor plant, if you don't water it for a few days, you could do this experiment at home, although your parents and guardians might be a little upset. It's starting to wilt and fall apart. The turgor pressure is leaving this particular plant. And that is where we are going to stop for today. And we'll pick up with part 3 and facilitated diffusion later. Have a good day.